All right. Good afternoon, everybody. Welcome to a cloudy but nice afternoon of organic chemistry, Chem 170, with your host, me, Dr. White. Today, we'll be finishing up the aldehyde and ketone problem set. And then, because I've taught this class before, good news for you, I know students have a lot of problems with certain general reactions in ketones and aldehydes. So we're going to go through some of those. Then afterward, we'll do the distillation lab. Exciting afternoon. All right, let's get started. And let me ask my thumbs up. Do you see? Well, let's go back ones. Yesterday I was talking about keto enol tautomerism, which I won't put on a test, but it's important to understand a very important reaction that I will have on the test, and you should know. Now, keto enol tautomerism. Anytime you see the word tautomerism, that means you have two different forms, and all you're moving are electrons and a hydrogen. And so that's a keto enol tautomerism. And as I discussed on Monday, for ketones and aldehydes, oops, got to turn on my graphics pad. All right, let's. For ketone or aldehyde, you have this equilibrium, which is it shifts back and forth between these two forms. This is called the keto form because it could be a ketone or an aldehyde. I don't know why they didn't call it the aldo form. And this is called double bond ene, OL, alcohol, OL, the enol form. So this is a keto enol tautomerism because if you look at side A and B, right and left, oh, by the way, later in the semester, I'll teach you the organic chemical difference between your right and left hands, but that's later in the semester. If you look at that, the difference between A and B, all I've done is move one hydrogen and electrons. And that's why this is tautomerism. Now, an amazing thing about ketones and aldehydes is the acidity of the alpha hydrogen to form the enolate anion. I'll show you this in a second on the board. See, it says C board down there, so I'll be doing that. The alpha hydrogen, I'll explain what is an alpha hydrogen, and a carbonyl compound is more acidic than a hydrogen on an alkane hydrocarbon atom. And this is due to resonance stabilization of the enolate anion. As I warned you before, this is hallowed ground for me because I did my PhD thesis on a very specialized enolate anion. So you're talking to a world authority right now on enolate anions. And Dr. White's smiling big time now. I love enolate anions. So what are we talking about? Now, if we look at writing a ketone or aldehyde this way, here's your carbonyl carbon. The carbon attached to it, this one, is called the alpha carbon. Next one is beta and so on. But for us, we only have to look at the alpha carbon. I'll never ask on a test, what's the alpha carbon? But you should know because I'll be talking about it. Now, the hydrogens on that alpha carbon are much more acidic than, say, propane. These hydrogens are not acidic. They're extremely hard to pull off, extremely. But you have this equilibrium, This is an acid-base equilibrium, and generally you'll react the base because normally you don't have a anion or cation floating around. And this is called the enolate anion. And this really doesn't happen, but this does. And you can look at this, and the question is, why can you pull this H plus, proton H plus, off the alpha carbon? And the reason is stabilization. The enolate anion, I can move the electrons there. Remember, it switches off for the slide. And form these two resonance forms. And these are both the enolate anion resonance forms. And when you can draw resonance forms of something, you make it more stable. When you make something more stable, it's more likely to go to that, easier. So the enolate anion is formed when you pull off an acidic hydrogen. That means you can pull it off with a base. And that's the enolate anion. Now, my PhD thesis dealt with a very specialized enolate anions, and most organic chemists, what I'm about to tell you, wouldn't even understand what I'm about to say, but I want to bring back a good old memory, and that is I work with kinetically favored cross-conjugated enolate anions. I'll say that again because it makes me feel good. I work with kinetically favored cross-conjugated enolate anions. And most organic chemists wouldn't even know what I just said because it's so specialized, but it's very important. And my understanding of enolate anions, my last patent used my understanding of enolate anions. So they are important. So what does this mean? Well, if you have an enolate anion, you've got here a negative charge on carbon. It's saying, I don't want a negative charge. We're something that's positive. Well, let's look. And that's the Aldol condensation. And Aldol condensation, now the switch is on. If I could turn a dial that only goes up to 10 to 100, I just did, hint. And the Aldol condensation deals with reacting an enolate anion where it reacts as a nucleophile. And what's a nucleophile? Something that's loves positive charge, nucleo from nucleus of the atom, positive, phile from lover. And just remember the carbonyl is slightly polarized, and therefore any nucleophile will attack the carbonyl carbon. Well, here's the Alvol condensation. First of all, why is it called an Alvol condensation? ALD from aldehyde, OL from alcohol. And that's how you got the Alvol condensation. Now you can use many different bases. I'm going to use sodium hydroxide, and I could really put down water because most of the reactions you're doing it, at least all the ones I've ever done, is solvent. There is a whole branch of solid state chemistry, but I've never worked in that. Never. All right, let's look at the aldol reaction. And I'm going to make it easy for you. You can have aldol reaction with ketones, with aldehydes. but I'm going to make it very easy. I'm going to do an aldehyde only for this class. Now, here's my alpha carbon. Now, historically, you'll either put a 2 there, or organic chemists won't even do anything because we know we don't balance things. We know it takes it. But on a test, I'll put 2 of the same aldehyde. That's my special gift to you. Now, the alpha carbon of a ketone or aldehyde, in this case, you'll form the enolate anion, and that will attack the other aldehyde. And why do you need the sodium hydroxide? Because that pulls off one of these to form hydrogens to form the enolate anion. Now, when that does that, you've pulled off from the first aldehyde, from the alpha carbon, hydrogen, H plus, so that's why it's only CH, not CH2. Now, this shows you that this will attack and bond to the other carbonyl carbon and open it up, and it opens it up to an alcohol. And what's attached to the second carbon, which I'll use 2 dots, will still be attached to it. And this is called your Aldol product. But most importantly, look what you've done. And this is the beauty, the strength, and the power of the enolate anion. You've made a carbon-carbon single bond. In one step, you've combined 2 molecules to make a very much more complex molecule. And unfortunately, there are other reactions enolate anions undergo that I am not able to talk about this semester because it's only one semester. So let's take a look at this. Oh, good news. I'll never put a synthesis problem for an Alvol condensation reaction on my test or final. That's cruel and unusual punishment. As you all know, the Supreme Court of the United States has outlawed cruel and unusual punishment from faculty towards students. And I don't do that anyways. All right, now how do we proceed? Oh, 2 of the same aldehyde. I have sodium hydroxide, and that's a base. And for this class, that's the only other base, the only base I'll use. There are many other bases you could use, but that's the one I'll use. Then we look at the alpha carbon. It will attack that, which is what we're seeing up here. And why? Because you're going to lose one of these, form an enolate anion, and that's what attacks. And therefore, the first aldehyde, I've removed one of the hydrogens, and here it is. And then, I'm running out of room, so I'm going to write it down here. This carbonyl carbon becomes, it opens up to an alcohol, and what's attached to it is still attached to it. In this example, R was methyl. And that's how you do the Alvol condensation. Now, I haven't talked about mechanisms, but let me give you a little peek of how this really goes. What I'm going to show you is just so I can have some fun and also show you something neat. Remember, Dr. White loves enolate anions, and I'm going to show you what's called the mechanism. If we look at the above reaction, when I react that with sodium hydroxide and water, the alpha carbon has acidic protons, and I'm going to form the enolate anion. I could draw another resonance form, but this will do. And now the second aldehyde is floating around. And the enolate anion says, wait a second, I'm looking for a positive charge. And I know the carbonyl carbon of that aldehyde is slightly positive. I'm going to go attack it. And it does. And it opens it up this way and forms a carbon-carbon. There's my first aldehyde. My alpha carbon attacks this carbon of the carbonyl carbon is second, opens it up to actually this salt or alkoxylate. What's attached to it is still attached to it. This is a very strong base with water, which is present right here, or alcohol even. It'll pull a proton. And that's how it's done. Now, will I ever ask this on a test, the mechanism? No, but just one reaction. Now we're getting into more complex things. I thought you'd see how things go stepwise. And Dr. White just had a lot of fun too, which is a good thing. Now, again, remember the aldol condensation. My gift to you is I'll write two aldehydes. In real life, organic chemists would just put one, put this, no, there's enough of both of these to react to do that. I wouldn't even put a two in front of there unless I had to balance it for charge weight calculations, which we're not doing in this class. So the alpha carbon has acidic protons, and you can pull it off and form the enolate anion, and that attacks the other carbonyl to form this carbon-carbon single bond, and the other carbonyl becomes an alcohol. And it's time for you to have some fun. What would be the organic product or products for the following reaction? And when I'm done with today's class, I'm going to go open my windows like I did yesterday and air my house out because it's so nice out. So it'll have that nice spring smelling, spring smell to it. Springish smell. Dr. White's inventing new English words all the time. Ooh, quick public service announcement from Dr. White. I think in about 2 weeks will be Passover. For those who know what it is, you know what I'm talking about. For those who don't, look it up on Google. But next week, the week before Passover, Jewel always has a sale on boxes of matzah. You buy them 5 boxes in a big box, 5 pounds for about $5-6. Normally, each 1 pound box costs like $4 or $5. And matzah is great to cook with. You can make matzah balls. If you don't know it, I'll tell you about that next week. And you can also use it for breading. A lot of secret chefs grind up and I make matzo meal. You just put it in a food processor, and then they use that as breading for things they fry and makes it more crunchier instead of using panko. And that's my cooking tip for today. All right, let's do this. And the question is, what's the organic product or products you would get? And you look at this and say, oh, look, here's an aldehyde. It's the same aldehyde again. And we're reacting it with base and water. Sodium hydroxide is a base. And that means I can pull a hydrogen off from the alpha carbon, which attacks this. The second molecule, aldehyde, this carbon becomes an alcohol. And what was attached to it is still attached to it. So if I look up here, what's our ethyl? That's one way, or you can just say the alpha carbon attacks that. You lose a hydrogen there, and you don't break carbon-carbon single bonds. And then the second, this carbon of the carbonyl carbon comes an alcohol. What's attached to it is still attached to it because you don't break carbon-carbon single bonds. And now I've made a new molecule. And I've made that special thing, very rare, very special, a carbon-carbon single bond from the alpha carbon of the first aldehyde to the carbonyl carbon of the second one, which becomes an alcohol. And if you wanted to, this is our R groups right here, still attached, as you see right here. Oh, this is a lot of fun. Let's do another one. But before I do another one, I realized I forgot to do a couple of public service announcements. So it's time for public service announcements from the management meet. First one is next Wednesday will be test 2. Test 2 will cover alcohols, epoxides, ethers, aldehydes, and ketones. I would hope by Friday sometime, maybe tomorrow I'll get it, because today I have my office hours and other stuff, but I will post and also send out an email with the points breakdown, how many pages, and what chapters, again, what functional groups are being covered. And that way you'll know how to study. Now, I will say there's a major difference between test 1 and test 2. And the major difference is the point breakdown. This will be in an email to you, but approximately, I got to write the test later today because every semester I write new tests. So let students keep their tests even if we were face to face. And that's why I have to rewrite it. But it's usually historically, and it will be 9 pages. I forgot how many problems. And this is the big difference. Now, about 65 points will be reactions. Give the product or product, and there'll be 3, not 1, but 3 synthesis problems. Give the starting materials. About 35 points will be nomenclature. No, there are 2 types of nomenclature problems. First one is, here's the structure, give the IUPAC name. And the second one is, here's the name, that can be both IUPAC or common, draw the structure. And finally, there'll be about 10 points. And since I haven't read it, this might vary by just 1 or 2 or 3 points, but essentially about 10 points on general knowledge. Now, I'm not going to ask how many bonds to carbon. I did that in test 1 already. But I will ask, did you happen to drive by a gas station and think about gasoline has ethanol? And what functional group is that? An alcohol? Did you? Do you happen to look at a bottle of vodka? You know, the good stuff, Absolute or Grey Goose. And by the way, the Costco French vodka is quite good too. It's almost as close to Grey Goose, and it's a lot cheaper. But if you're too young, don't buy it. But anyways, that's got ethanol too, which is an alcohol. Do you happen to look at a bottle of rubbing alcohol? And that's got isopropyl alcohol or 2-propanol, and that's an alcohol. Or do you happen to remove your nail polish with nail polish remover and looked at the bottle and see that's acetone, that's a ketone? You should think about chemistry, organic chemistry outside the classroom because it's everywhere. It's fun to think about. And that's that. Oh, one other public service announcement. My other class, the other school, I had a student who had a computer breakdown, and she had a lot of stuff on her hard drive, like her labs and her notes and all that. And she doesn't know if she's going to get it back. And I told her, we can still watch the videos. Anything you need, I'll help you with. But what I told the whole class this morning, I'll tell you, you should back up things. Thumb drives, they're cheap now. They're inexpensive. They're good insurance policy. This one is a 256 gigabyte hard drive. And what you don't know, but I'll tell you is your grade books, they're not kept on D2L. I just put that there so you can see your grades. Your grades are kept in a spreadsheet on my computer behind me. Every time after I enter any points, like for a lab or test, I back it up on one of these. The whole that, and I also have the whole course, all the lecture files, labs on here is backup. Now, interesting thing I found, pill container, empty one that is, makes a good travel protection. And also lanyard, that means I'm not, where did I go? Now, quick little story, do I have time? I do. And that is, when I was working for a company called Unichem Chemicals, this is back in the late 80s. Oh, I shouldn't have said that. But anyways, a long time ago in a galaxy far, far away, I was a senior manager. I was in charge of research and development, also quality control for the plant on that site. It was by the Stockyards race 35th and Racine by old Chicago baseball park. And we were part of, we being Unichem, part of Unilever, which is a monster international company. Lipton Tea is Unilever, Green Giant is Unilever, Lever Brothers that makes Snuggle is part of Unilever. Unichem got sold out a couple of years ago, but anyways, we were part of that. And twice a month we'd have a senior managers meeting, and each division or company, they were called, was operated like a separate company, even though the CEO of Unilever controlled everything. But still, each were almost like, and we had our own president and different officers, and I'd be at that meeting with my boss, who was the vice president of technical, which was I reported to him and the plant reported to him. And we got a new CFO, chief financial officer, from a sister company to help us out because Unichem was new to Unilever, and he was transferred from Lipton Tea. I'll tell you another day how I got in trouble big time about Lipton Tea, but not today. I'll have to wait for that. And we're in this management meeting, and he's new, and he's talking to people. He's not new in terms of he had worked a number of years at Lipton Tea as their CFO, chief financial officer. And the first thing he said in the meeting was, and he was new, he said, can someone tell me how we back up our computers? And back then we had the tapes. I don't know if you've ever seen the old tape drives. Then it wasn't old. And the president said, oh, we back it up and we keep it in the vault in the main office, which in the building we were in. And the CFO said, and his name was, how do I remember, Joel, said, no, we've got to make another backup and have it off site. And the president asked why. He said, well, if this place burns down, you've lost all your information. And he said, well, the vault is supposed to be fireproof. And Joel said, you want to bet your company on that? And the president said no. And Joel went ahead and got a monster safety deposit box. I never saw it, but it was described to keep backups of the tapes made monthly. So back up your stuff from your home computer, and it's a good insurance. Those cost the 256 gig, which most of you won't need. I like overkill. I'm a tech freak. It's about $35 just about everywhere. And you get smaller ones for cheaper. It's cheap and good insurance. All right, let's get back to the Alvol condensation. Let's do another one. And here's one for you to have fun. What would be the organic product or products of the following? I should mention, I might have, but if I didn't, I'll do it now. I will never on a test put a synthesis problem using the Aldol reaction. That's truly cruel and unusual punishment. And while you're working on that, I have some really good news. All the snow is gone on my property. Yay! Spring is coming, which means I better order my seeds to plant. I usually plant basil, uh, usually dill, and I'm thinking what other things I'll plant too, certain herbs, other stuff like onions, tomatoes, and all that. No, I don't have enough area to grow those. Anyways, I can buy them at my local supermarket, Valley Produce. In case you haven't figured it out, we're doing some really sophisticated organic chemistry now. If I look around at the videos, it looks like not anybody's in serious pain or distress, which is a good thing. All right, let's do it. Well, wait, I haven't done this. Let's try this. Use the power of Zoom meeting. And it looks like everybody's done. So I better get to work. All right, let's look at this. How do you determine what's the organic product or the products are the following? I look at the first thing and say, oh, wait, this is an aldehyde. And I'm reacting with base. Here's the same aldehyde again. This is an Alvol condensation. Oh, I should mention another popular base is potassium hydroxide. I usually stick to this one. Why? It's cheaper. If you're working in industry, you know prices like that. And the base will pull off one of the hydrogens from the alpha carbon to form the enolate anion, which will attack the other carbonyl carbon. And so you don't break carbon-carbon single bonds. Here's the first aldehyde. It attacks the second one, opens it up to an alcohol. And here's what you get. Now, one way you can say this is my R, same thing here, or you can say the alpha carbon attacks this, and therefore now I'm going to make the world's longest carbon-carbon single bond because the ring's in their way here. And this opens up from the second aldehyde to an alcohol, and what's attached to it is still attached to it. That's a 6-membered ring. Hold on. That's better. And notice the new molecule you've made from simple molecules. This new molecule is quite complex. And that's the beauty and the strength of the Alvol condensation and enolate anions. Now, there are other things you can react enolate anions with to make carbon-carbon single bonds, but unfortunately, I won't be covering that because there are other things I like to cover in this class that are important, such as later on, I like to spend more time with things like fats and oils, carbohydrates, proteins, you know, the good things in life. Any questions on this? All right, now, as you know, I've taught this for more than once, twice, 3 times, well, a number of times. And I've noticed over the years, there's certain reactions, especially in the ketones and aldehydes chapter, that students historically have difficulties on test 2. And so that you won't have those difficulties before and after today's break, we're going to go through those areas again to give you some more practice so you'll do well on test 2. And more importantly, you'll also learn it well.
Dr. White?
Yep.
I have this page that I don't have anything on. I don't.
What I was trying to show you there was, Tom, that that's how a nucleophile, in the case, and we're going to do that reaction sort of just now, a form of that, where the nucleophile attacks the carbonyl, it opens it up, and a proton from the nucleophile attaches to the carbon to make an alcohol. So hang in there for about
Okay.
8.10 seconds. That doesn't work out. 10.8 seconds, and I'll show you. And remember, all questions are good questions. And here, this is a reaction to form a hemiacetal or hemiketal. And here you have an aldehyde or ketone. When R prime is hydrogen, it's an aldehyde. When R prime is carbons, it's a ketone. And think of this, this is the Nu part, and this is the H plus part. And see how the H plus goes to the oxygen and the Nu goes to the carbonyl carbon on that, Thomas? And that's why I had that earlier in general, to give you an idea of what's going on when we first started talking about it. So here's the general reaction, but I'm going to let you try one. And the question would be, what's the organic product or product? And the reason we're doing these types of reactions is for you to learn these general reactions that organic chemists use to build molecules we use in our daily life. And later in the semester, I'll show you some, such as your plastic bottle, the soap you use, fabric softener, a whole bunch of stuff. And I've already shown you some in previous chapters. It's my phone. Oh, no, it's not the White House. It's not the Senate or Congress. So I'll let my voicemail pick it up. One more ring. Nope, it stopped. All right, let's do this. And the question is, how do you do this? You look at the molecules and look for what's different. What's not a carbon-carbon single bond, carbon or hydrogen should get your attention. Right here, I have a carbon-oxygen double bond, and that's a carbonyl. It's got carbons here. That's a ketone in a ring, but it could have been an aldehyde too. And what do we have here? Carbon, carbon, carbon. Ooh, hydroxyl group on a carbon. That's an alcohol. And notice you have acid catalyst. Keep your eye on the carbonyl carbon. That's where the fun is. What's attached to it stays attached to it. This becomes a hydroxyl group. And you also have an oxygen with our group. And this whole ring are these two together connected. So therefore, they're still attached to this carbonyl right here, carbon. Now I'll still have my ethyl group here. This thing 6 months ago, if I said ethyl group, you would know what I was talking about. And this carbon right here, which is this carbon, will have a hydroxyl group, oxygen. What's my R? The carbon with the hydroxyl group is the carbon this oxygen is bound to, in this case, the end of 3 carbons. I was running out of room right here. That's why I stuck it up like that. And that's the product you get. And hemi, in this case, ketal, which I'll never ask you to identify. Let's do another one. Again, these are reactions students have difficulty with on test 2, so I'm giving you a little extra practice. And if we take an aldehyde or ketone, when R prime is hydrogens and aldehyde, when R prime are carbons, it's a ketone reacted with not one, but two molecules or moles of an alcohol, acid catalyst. Keep your eye on the carbonyl carbon. That's where the fun is. And you get, in this case, an acetal or ketal. In case you forgot, I'll teach you more and specifically, this is the reaction Mother Nature uses to make starches. So let's have you try one. And there's one for you to try. All right, I think everybody's done. Let's do this. All right, now, if we look at this right here, the question is, what's different? Ooh, what's not hydrogen? What's not carbon? An oxygen double bond to carbon, carbonyl. Carbon double bond to oxygen. I've got a hydrogen and carbon to it. That could be R prime, or in this case, hydrogen. And this could be a ketone or aldehyde. When you react two of, what's this? Carbon, carbon, hydroxy group, alcohol, acid catalyst, what do you get? Keep your eye on the carbonyl carbon. What's attached to it? R prime or H. R double prime is still attached. It has a hydroxy group. It's not really an alcohol. Or wait, I made a mistake. Mine is still on the last problem. And you have two oxygens, each one has R. Now, if we look over here, R prime is the hydrogen. R double prime is methyl. R is ethyl. So I'm going to keep my eye on this carbon, which becomes this carbon. I'll have two oxygens. My R prime is hydrogen. My R double prime is methyl. And my R group, let me move myself out of the picture here. Whoop. And that's my R group. And this is the molecule I made. In this case, it's called an acetal. And we'll learn more about acetal and ketals when we talk about carbohydrates, because they're quite important. And that's how you do it. Oh my goodness, time flies when you're having fun with ketones and aldehydes. It's time for Dr. White to do a little stretching. I'll see you in 5 minutes at 1:55, and at that time we'll continue. All right, let's get back to work. Ring, 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 ring. Oh, I know what to get you back. All right, let's get back to work. But before we do, a quick little thing. Have you ever wondered what this picture is? Later today, you'll find out. All right, let's get back to some important things you should practice for test 2 because students historically have problems with this. And let's continue. And if we have a hemiacetal or hemiketal, our prime can be carbons or it can be a hydrogen reacted with acid and water. Remember, you can find acid and water in your stomach, and we'll come back to this reaction. We talk about how you digest carbohydrates. And what you get back is the ketone or aldehyde you would have used to make the hemiacetal or hemiketal, plus the alcohol you would have used to make that. And remember, this carbon becomes this carbon. And the giveaway is this is one of the only 2 places in all organic chemistry where you have 2 oxygens single bonded to carbon, the same carbon. And this is hydrolysis, acid hydrolysis of a hemiacetal or hemiketal. And here's one for you to try on this sort of semi-overcast, but really nice and warm. I don't know, maybe I'll go outside a little while after class, soak in some of the spring weather before it gets cold again. It is Chicagoland. A few people are still working, so give you a little more time. Quick question for all of you, and give me a thumbs up. You can't do thumbs down, but do you like when I'm doing the polling? To see if you're done, sort of. All right, well, since How many would like me to go back to the thumbs up? All right. In that case, did I tell you that I run a democratic dictatorship? I make the final decision, but I'm going to take your vote and we'll do thumbs up from now on, rest of the semester. All right, let's get to work. Question is, what's the organic product or products that are following? And we look here and say, what's different? What's not carbon? What's not hydrogen? Ooh, oxygen. No, two. It's the same carbon, single bonded. And on this oxygen, I have carbons. And on this carbon with two oxygens, I have a hydrogen. I could have had carbons, but I have a hydrogen, I have more carbons. And this is a hemiacetal. It could have been a hemiketal, acid and water. And keep your eye on this carbon with two oxygens. It becomes this carbonyl carbon, carbonyl carbon, double bond to oxygen. And you get a ketone or aldehyde. And this R group here becomes the alcohol you would have used to make this, going back. And now if we look at this, what's our double prime? What's our prime? What's our, and now this carbon right here, what's attached to it? Our prime, our double prime. Remember, our prime and our double prime are like in math, X and Y, and Z for R, I guess you call it. And R, which goes here, is methyl. So we get methanol. And here's what you get. Remember, the carbon in R, in this case, we only have one, that has the bond to the oxygen is the carbon in R that has the hydroxyl group. Another one I'd like to cover, and this one, students, I don't know, I think there's something written here in secret language. I don't like doing this. I'm going to get it wrong. Hopefully it doesn't say it. And this is acetal or ketal, which we'll come back to because this is the first step that happens in your stomach when your stomach is breaking down starches, which are carbohydrates. And if you look at what happens, keep your eye on the carbon with the two oxygens. Again, guess what? You get the same products as the previous reaction. This carbon becomes this carbon. What's attached to it is still attached to it. Each of these OR become an alcohol. Since I only ask for give the product or products, you don't have to balance it. But for those of you who do, and I put it in quotes, meaning you don't have to, you could put it two there, and that's what you get, the aldehyde and ketone and the alcohol you would have used to make that, which we just went through earlier today. So here's one for you to try. And due to the universal disfavor of the polling, I'll be going back to thumbs up when you're done. Oh, I just thought of something sad, and I actually knew someone who had it. If you don't have a thumb, you can use your finger, or you can use the emoji too. Actually, I did know someone who lost one of his thumbs in a serious farm accident. in Iowa. He lived in Iowa. Oh, I see one also. You can also type and send a chat message, thumbs up. I think everybody's done. Oh, wait, maybe not. I'll check the other part. Anybody need more time? Nope, I think everybody's done, so I better get to work. Now, I keep on saying this, but it's one of the most important things in organic chemistry. Look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen should get your attention. Ooh, oxygen, oxygen, both single bonds to the same carbon. And then carbons on those oxygens. And that carbon has carbons here, which I'll call R prime and R double prime. Now, R prime could have been a hydrogen, but it's not. Acid catalyst and water. And you keep your eye on the carbon that has the two oxygens, becomes a carbon double bond to oxygen, carbonyl carbon. What's attached to it, R prime or hydrogen, R double prime is still there. Then my R group becomes an alcohol. And for those who must, you can put a 2 there. Well, the ring is both R and R prime and R double prime. What's attached to it comes along because you know you don't break carbon-carbon single bonds. And the carbon that had the two oxygens, this carbon in the ring, is now this carbon double bond to oxygen. And then here's my R group. And therefore, I get ethanol. And for those who must, you can put a 2 there. I wouldn't. But then again, I'm a lazy organic chemist. And that's how you do that. And always remember, there's no such thing as a dumb question. So if you have questions, always feel free to ask. And let's go another one that students have difficulty with. Making the Grignard reagent, students never have trouble reacting it with remember, this is a two-step reaction. Oops. First step, add this. Oh, it's a Grignard. Remember, X can be chlorine, bromine, or iodine. And second step, you add acid and water. Keep your eye on the carbonyl carbon because that's where the fun is. What's attached to it stays attached to it. R prime or hydrogen, R double prime. This opens up to an alcohol, hydrox group on a carbon, and the carbon that was the carbonyl carbon is now bonded to our R triple prime, and you've done something very special, very rare, and very powerful. You've made a carbon-carbon single bond. And here's one for you to try. Have fun. All right, everybody done? Thumbs up, people. Thumbs up, people, without your, oh, I see some of you found the emoji. I guess you're all done. Let's do this. Now, look for what's different. I think I even got my chat thumbs up. I do, from Joshua. Thank you. All right, what's different? And I'm going to move up here. Ooh, oxygen double bond to carbon. It's got a hydrogen, but that could be our prime. And it's got carbons here. We have an aldehyde, and it could have been a ketone. Carbon, carbon. Ooh, magnesium halide. That's a Grignard. Remember, X can be chlorine, bromine, or iodine. In our case, it is iodine. And second step, acid and water. And keep your eye on the carbonyl carbon because that's where the fun is. And what's attached to it, either R prime or R double prime, and R double prime, it opens up to an alcohol, and the Grignard forms that special thing, a carbon-carbon single bond. Well, here's my R prime, here's my R double prime, and here is my R triple prime. If you're wondering, the most I've ever done in not in a classroom, oh yeah, in a classroom, no, in a lecture, symposium, R triple, quadruple prime. After that, you start using numbers or letters. But anyways, what's attached to the carbonyl still attached to it, which becomes this carbon. And that's R prime, hydrogen, R double prime is methyl. You have an alcohol, hydroxyl group. And what's my R triple prime? N-propyl, the carbon with the magnesium halide on it, MgX, is a carbon bonded to the carbonyl carbon, in this case, the N carbon. And in one step, we made a much more complex molecule. Oh, let's do this once more. I like this. Now, sometimes when the Grignard is big, you put it here instead of a sec above the arrow. I just gave myself more room. And there's, let's just redo this so it looks nicer. And second step, acid and water. And it's your turn. And remember what you asked to do. When you're done, give me a thumbs up. Oh, good news. Everybody just gave me a thumbs up, so I better get to work. If we look over here, how do we determine what's the product of this reaction? We look for what's different. What's not a carbon-carbon single bond, what's not carbon or hydrogen, gets your attention, gets mine. Ooh, oxygen, double bond to carbon. It's got carbons here and carbons here. It's a ketone. Could have been an aldehyde. Ooh, Grignard, first step. Acid and water, second step. And remember, X can be chlorine, bromine, or iodine, one of those halogens. And keep your eye on the carbonyl carbon. This carbon becomes an alcohol. What was attached to it over here is still attached to it. And now we form that special carbon-carbon single bond from the R group of the Grignard. Remember, the carbon in the Grignard with the MgX is the carbon in R triple prime that this carbon is bonded to. So if we look here, this is our double prime and R prime connect together. It's a ring. Here's the carbon here, which is this carbon, which becomes this carbon. So I'll draw my ring, have my methyl group. This carbon right here, you don't have to do that, will have a hydroxyl group. Doesn't matter which side you put the hydroxyl group, right or left. And notice our triple prime, 3 carbons. My Grignard is to the center carbon. So therefore, 3 carbons, the center carbon is bonded to my ring. And now I've made this very complex molecule. And that's how you do a Grignard. And those 5 reactions historically students have difficulty with. I highly recommend you practice them. Speaking about practice them, next Monday, I will go through the ketones and aldehydes problem set. I highly recommend that you do them before I do. That will help you do better on the test, and it'll also help you learn the material, which is what I want, and that's a good thing. Now, also next Monday, I will do my world famous review for the next test number 2. And we'll do other stuff too. You know something? I need a pick-me-up. Let's play that fun game, circle and name the functional groups, 2 points each. And there you go. Have fun. Remember, you're not asked to name the molecule. Just circle and name the functional group, 2 points each. And while you're playing that fun game, I'm going to sneak out into the real world. All right. Quick, stop the presses. That big COVID bill has been passed by both the House and the Senate and is now going to President Biden to sign. I don't like to bring politics or anything, but I think that's a good thing for all of us. But let's get back to playing that fun game. Circle and name the functional groups, 2 points each. And when you're done, don't forget to give me a thumbs up. For those of you who know Morse code, you can send that. Oh, wait, I don't know Morse code, so never mind. And don't forget, you can see me live, well, actually not live, recorded, but on the Chem 170 YouTube channel, where I'm an international star, only in my own mind. All right, I think everybody's done. Let's do this. All right, how do you find the functional group? You look for what's different. What's not carbon, what's not hydrogen. Ooh, an oxygen there on a carbon. And that's, in this part you don't have to, but alcohol. Remember, a methyl group is not a functional group. Oh, oxygen here and one here. If I look at this one, it's an ether. If I look at this one, what do we have? R group carbons, carbonyl, carbon double bond, hydrogen, and that's an aldehyde. If we come over, ooh, an oxygen there and one there, that should get my attention. What's this? ROR prime, and that's an ether. Ooh, carbonyl, carbon double bond to oxygen. Carbons here are prime, carbons here are double prime. That's a ketone. And there you go. Ooh, D. I think I threw everything in but the kitchen sink here. Here's an oxygen, here's an oxygen, here's another one, and here's a fourth one. Well, this is an ether. Hydroxyl group on a carbon. Alcohol. This is a hydrogen. R carbonyl hydrogen. This right here is an aldehyde. I apologize for this being so crowded. I should have spaced it out more. And finally, this carbon to this oxygen right here. It's a ketone. Give you a chance to copy down things if you're copying down things. If not, remember, by tomorrow sometime or Friday at the latest, I will have this on the YouTube channel. All right. I hope you all enjoyed playing that fun game, circle and name the functional group, 2 points each. And now, all right, it's lab time, and let's talk about today's lab. What if you had a mixture of liquids and you wanted to purify it, or a liquid that was impure? How do you purify it? In organic chemistry, we use what's called a distillation. And a distillation is a way of purifying liquids. And both in graduate school and in industry, Dr. White's done a lot of distillations. The smallest one I've ever done is about 3 milliliters. That was very tiny. The biggest one I supervised was in a chemical plant that was about 250,000 pounds. That was not very tiny, it was a lot. But anyways, distillations are a way of purifying things. Now, give me a second while I just clean up here. Don't forget to hand the lab that's due today or tomorrow, please. All right, now, if you look at the lab, everybody see distillate purification by distillation on your screen? Thank you. Distillation depends on liquids that boil. And when a liquid boils, the vapor pressure of the liquid is equal to the atmospheric pressure. The temperature at which that happens is called the boiling point. And how do you see that? When a liquid boils, vapor of the liquid collects to form bubbles. And these bubbles rise to the surface of the liquid, collapse, and the vapor continues to rise to the top of the liquid. If you were to cool that vapor, it would become a liquid again. We call that it condenses. All right, I'm going to assume each and every one of you has seen water boil. Have you all seen water boil? I think so. You know, you see the bubbles in the pot. Let's talk about that because it's an important safety feature. Oh, I should warn you, artwork from Dr. White, you feel free to laugh your head off. That's a beaker. And for now, let's just have water in there. And underneath, I have a hot plate. In an organic lab, you never use an open flame. And a hot plate is just a way to introduce heat to the water. And after a while, you'd see bubbles in here. Now, this is in a lab, we do things in glass. An important thing you should know about glass is it's very smooth, even with scratches. Now at home, you're used to using a metal pot or pan, and those, it feels smooth, but no, a metal pot or pan is rough like the Grand Canyon. It's really rough, even though it feels smooth, it's rough. Well, why is that important? Because when you boil things and you form bubbles in a pot or pan, you'll have a place where, all right, oh, I'm getting better. This metal is rough, so you can form bubbles on the surface that come up, assuming you had water in there. Now, glass is not rough. So what happens is you get these monster bubbles that come up and splash all the liquid all over the place. And we have a special name for that. And that's called bumping. And bumping is not good in a lab doing a distillation or anywhere you do a distillation. So how do you do that? We put things in there that are very rough and inert. At COD, we use marble chips. At ECC, we like to spend a little money on our students. We use carborundum, a very inert, rough metal little chips. And you only have to put about 3 or 4 of those. By the way, how many of you ever heated up something in a microwave in like a glass measuring cup and it's popped out of there? That's because it bumped in there. And I usually, if I'm going to do a lot, big, say a measuring cup of water, I'll put 1 grain of rice in there to make a nice rough surface so it doesn't bump. But anyways, when you do boiling of any liquid in glass, you have to put in your boiling stones or boiling chips. Either way, we use the stones, carborundum, or chips, marble is another one. And you put only about 3 or 4 of these. This provides a rough surface that keeps your bubbles tiny. And that's an important safety feature. All right, what just happened? Okay, now, how do we distill something? In other words, separate different liquids that have different boiling points. You use a distillation apparatus. Now, here's an example. Whoop, did it again. I don't know why it does this at times. Hang in there. All right, sorry about that. Everybody see the distillation apparatus on the screen? And in real life, you would be setting this up. And distillation apparatus has various parts to it. One is the round bottom. And this is a round bottom because it's a glass sphere and it's round as bottom. Now, if you notice right here, and here, and here, these are called ground glass joints. And if we were at ECC, I'd be teaching you how to use high vacuum grease to lubricate it. You'll always lubricate it. Now, you have a still head or distillation head, and then a thermometer adapter and a thermometer. Now at ECC, a couple of years ago, we spent some money and we use now thermocouples hooked up to a box that gives you the temperature. Now the distillation head connects to the condenser. How many of you have ever in the midst of the winter taken a real hot shower or bath and your mirror gets all fogged up if you don't have a good vent in there? In fact, about 5 years ago, the vent died. And I also had some insulation work, and that company put a real powerful new vent in there. And what happens is the cold mirror, the vapor, water vapor, moisture from your shower or bath hits the cold surface and becomes a liquid again, sort of. And that's what fogs up your mirrors. and that's condensation. Well, we use a condenser. And here it is, and it has a center tube that's separate from a surrounding outer tube. An important thing you should know about a condenser, it's always water in at the bottom and water out at the top, which means this goes to the sink. You put tubing on there. Why? Because this whole outer area fills with water, and it's cold water, and that causes any vapor that when this is boiling to come here and condense into a liquid. And the liquid comes down here to the condenser adapter, also called the vacuum adapter, and drips down into a container. And by having different boiling points, you can separate things by heating slowly. Now, important other thing, safety consideration. How many of you have ever made rice or boiled noodles? Do you want to put the water in the pot you're cooking in all the way to the very top of the lip? No, because it will boil over and you'll have a mess. Guess what? Same thing's true in organic chemistry and distillations. In a round bottom, you never fill this. In the video I'm going to show you, they say half. In real life, you never fill more than than 2/3. Otherwise, it can bump or boil over, which won't be good to purify it. The other thing, an important safety consideration, you never take the round bottom or let it go dry. Why? Because there might be residue in there with the excess heat will explode, which is not good. So you never let this go to dry. And when we do the lab, I make sure there's enough of the compound we'll be distilling left in the round bottom. And that's today's lab. You'll be distilling hexane. Now, important thing, this is called the distillation apparatus. How many of you ever seen a TV program, and I've watched it a couple times, and I get, I don't want to watch anymore. I'm getting frustrated because I could do much better. The moonshiners, I don't know what's the name of it on the history, where they have these guys who are making illegal whiskey called moonshine. And how are they using that? They say, we're using a still. That's shorthand for distillation. What they're doing is in a container, they put various things, I'm not going to tell you because it's against the law, but to make ethanol by fermentation. And then they take that and strain out any solids and put it into a distillation still, heat it up, and take the ethanol, and some water comes over too. That's a whole other area called steam distillation, which I'm not going to get into in this class. And they purify and get the alcohol out of what's called the mash, their liquid where they fermented different things to make ethanol. They sell it as moonshine. Don't do that at home, it's illegal. Don't do that. And that's what we're doing, but we're not using it with alcohol. No, 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 no. All right. Everybody see YouTube on your screen? Oh, no, I better hold on. Now do you see YouTube on your screen? Thank you. All right, let's watch a nice video.
Distillation is a separation technique that separates compounds on the basis of their boiling points. First, a round bottom flask is clamped to one ring stand. The flask must be large enough that the solution does not take up more than half the flask. A stir bar or boiling stone is added next. Here, you can see one single boiling stone.
They're doing this wrong. You should have a powder funnel there, not like that.
The solution to be distilled
This
is
is
added
wrong
after
too.
that.
You should use a funnel.
Once the solution has been added, a three-way adapter is attached to the round bottom flask.
Which has been
Notice
lubricated.
that no ket clip is added, as the high heat of the distilling vapor can melt it. On a separate ring stand, clamp the condenser sideways. A vacuum adapter is attached to the lower end of the condenser with a ket clip.
We don't use those clips because you don't need it if
Ensure the openings of the condenser are pointing up.
they can still be down. Listen carefully.
Move the ring stands together in order to connect the three-way adapter with the condenser. Secure the connection with a ket clip.
We don't need those.
A beaker is then placed under the open end of the vacuum adapter in order to collect the distillate. Attach the hoses to the condenser.
This
The
is
hose
important.
attached to the water is connected to the lower opening of the condenser, and the spare hose is attached to the upper opening of the condenser and directed to flow into the sink. When done correctly, water should flow up the condenser and into the sink. An iron ring is used to support the heating mantle,
We
which
use
is
a
moved
lab
upward
jack.
to snugly cup the round bottom flask. The cord of the heating mantle is tucked under the ledge of the hood and then plugged into the outlet under the ledge, where it can be controlled by the variac dial. The distillate should drop at a rate of 1 drop per second. If it is dripping faster than that, as shown here, the variac dial should be turned down.
And let me show you a second one.
When performing a distillation, first the condenser is filled with cold
Everybody
warm
see
water.
YouTube?
Next, heat is applied to the mixture which is to be distilled. The mixture is heated until it boils, and the hot vapors will travel up to the distillation head. Measuring the temperature of the vapors helps us to identify the liquid being distilled and will help to confirm its purity. If the vapors are pure, they will have a constant temperature equal to the boiling point of the liquid being distilled. As the vapors travel into the condenser, they will be cooled and will liquefy. The liquid droplets, called the distillate, run down the condenser and are collected in a receiving flask. A liquid can easily be separated from non-volatile contaminants by using a simple distillation apparatus such as this one. Since the non-volatile components in the distillation flask will not evaporate, the vapors and the resulting condensate will be pure. This animation indicates that the temperature of the vapors measures the boiling point of the liquid. What exactly does boiling point mean?
Yeah. Tom, go back and play it again. The link is in the lab. Sorry about that. I heard it, but I don't know why it didn't come through clear on your end. But anyways, quick question. Everybody see the lab now again? Thank you. All right, now, you should never let your distillation flask go dry and stop the distillation when there's in there. Now at ECC, we don't have a separate variac that's part of the hood. We actually have a separate one that's a standalone, but you control the heat. And what you would been doing would be put in 30 milliliters of hexane, even though it's pure. This is just to get a feel for how to do distillation. I would show you how to set it up. Then I check it. You turn on the water. If you turn on the water too quick, it'll pop the hose and you get a nice unexpected shower. Not good. And that's why I warn students, you slowly heat up the heating mantle, set it about halfway, and collect the hexane that comes over in those drops and record the temperature with the distillation apparatus thermometer. We actually now use a thermocouple when the listed volume and the data sheet are collected. And the last sample, turn it off and clean up. Now, here I give you the data. Now, how do you determine the boiling point of a liquid? That's when it levels off, and it's about the same for a while. That's the boiling point. And I gave you the data. In real life, you would find this out yourself, unfortunately. And here are the questions to answer. And it's time for show and tell. Now, if you see this picture, see it? What is that? Well, after I used the following in grad school, not the one I'm going to show you, because a couple of years ago, I found out someone, well, I happened to look and they were selling it cheap on eBay, and I have my own distillation head. This is for very small distillations. Here's the condenser right here, water in, water out. This is for pulling a vacuum. Thermometer goes in here, and I have, which I got on eBay, a small 15 milliliter. I've used from 5, which is much smaller than this, up to 100 on here. And this is a ground glass joint, which you lubricate, and you put another one of these here, which you can change. And this is a distillation head. Like I said, I got a good deal on eBay. In real life, new one of these costs about $150. And isn't that cute? And such fond memories. They were so nice to me. Mine was. I used it a lot to purify things before I could go on to the next reaction. And when you're working with certain things, you're working with small amounts. Also worked with bigger ones too. And that's today's lab. Don't forget, 1, lab due today, do it. If you haven't been handing in labs, next week I'm going to send out an email about amnesty program I'll have for labs for any of you who are gotten behind, and hopefully you'll catch up. Don't forget, next Monday, I'll go through the aldehydes practice problem set, so make sure you do it. It'll help you on the test. Next couple of days, I'll put out information about test number 2, like I did for test number 1. Also next Monday, I'll do my world famous and backed by popular demand, because remember, all of you asked me to do it again for next test. So I'll be backed by popular demand, my review for the next test. Don't forget, tonight, I'll have my office hours. If you have any questions, come on by. The link is in my syllabus and also on the front page of Chem 170 Introduction and D2L. And also, I think I mentioned Monday, but I'll say it again, my special public service to you. If a couple of you want to meet together on Zoom, come to my office hour. I'll set up a breakout room and you can stay there and work together. I'll stay out of there unless you invite me in. And with that, I'll say, gang gesund, be healthy. I'll see you on Monday. Bye, and I'll stick around if you have any last minute question.